Hello, my name is Dan Brunner, and in this video, I'll be going over how to solve problem 4.065 from Chapter 4 in the Fundamentals of Mass and Heat Transfer textbook. So looking at the problem statement, we're given that we have a long bar with a cross-section of zero point 0.2 by zero point 0.3 meters. This bar has a thermal conductivity of 15 watts per meter Kelvin, and it's subject to a variety of boundary conditions. The first of which is that the top and bottom surfaces are maintained at a constant uniform temperature of 200 degrees Celsius. The left side of the bar is insulated, and the right side of the bar is exposed to a fluid that has a convection coefficient of 60 watts per square meter Kelvin and an ambient temperature of 30 degrees Celsius. And so the whole idea of this problem is that we're going to be using a numerical technique, namely the FDM method with a grid spacing of 0.05 meters to determine the temperature distribution in the bar and the heat transfer rate per unit length between the bar and the fluid. So we're given all of the constants that I just mentioned from the problem statement. And what I did is I separated this bar into 35 distinct nodes. You could also recognize that there is symmetry in this bar and only include the top or bottom half and then multiply the final solution by 2. That method actually does reduce the computing power and the number of temperature equations that you'll be solving for. But I just did the full 35, and it doesn't really matter because you'll end up with the same result regardless. So again, we're trying to find the temperature distribution in the bar cross section and the heat transfer per unit length between the bar and the fluid. And the assumptions that we'll be making to help us solve this problem include that we're at steady state. We have an adiabatic left side. The top and bottom edges are isothermal. We have 2D conduction. The bar has constant properties, and there is uniform constant convection occurring between the bar and that ambient fluid. So to solve this problem, we'll be using 3 main governing equations, the first 2 of which here are sort of built into the finite difference method approach. The Fourier's law equation and the first law of thermodynamics, or our closed system energy balance, are used to derive the equations that are given in table 4.2 for a variety of node configurations. And so I won't go into those derivations in detail, but we will discuss those nodes a little bit later. And then for the second part of the question, we'll be using Newton's law of cooling to solve for the heat transfer rate per unit length between the bar and the fluid. So a little bit more about those node configurations I had just mentioned. Ultimately, there are 3 node configurations from that table 4.2 that we'll be looking at. Some of the configurations are mirrored on, both sides of the bar. And for example, this corner node right here obviously appears 4 times. But the general equation is the same for each of those separate occurrences. And in total, we have 9 possible node configurations that we could look at. What ends up happening, due to the constant surface temperature boundary condition that we're applying, is that this corner node essentially becomes insignificant. And so we'll only be considering the right side surface node, the left side surface node, and then interior nodes, such as the one that's given in case 1 here. And so, like I just said, we've got that left side configuration, right side configuration, and the center interior node configuration. And we can program, we can create a MATLAB script to have all of these temperatures automatically calculated for us if we'd like. What is important to note here is that this left side configuration actually has the same exact equation as the right side here, um, except for the fact that this right side has convection. And in table 4.2, you'll actually see a little superscript with a note that says that you can just set these convection coefficient terms equal to zero, and you'll end up with the proper equation for an adiabatic boundary condition. And that's given over here on the left side. And so if I open up my MATLAB script, I'll show you what I did here. So I, of course, first initialized all of the constants and model parameters. Um, the spacing is given by the problem to be 0.05 meters. I calculated the total number of nodes in this bar. Again, I didn't uh, assume that the top and bottom are symmetric, and so I just calculated the full 35. You could recognize that symmetry and simplify the number of equations that you'll need, but you get the same result regardless, with slightly more computing power if you go about it my way. Um, and so in the textbook, you'll read about how you can establish these matrices. The first being this A matrix, which contains all of the coefficients of the temperatures that are given in your temperature vector right here, this T vector. And so when you multiply your A matrix and your T vector and set that all equal to this C matrix, you have an equation, and eventually you can solve for, you can take the inverse of the A matrix, multiply that on both sides, and solve for your temperatures that are in your temperature vector. This C matrix contains all of the constants that could be brought over to the other side of the temperature equations. And again, these temperature equations all come from those node configurations that are given in table 4.2. And so, like I was mentioning before, I went through and automated this process. And so I established the boundary conditions. The top surface is given by n equals 1, based on the way that I created this code. The bottom surface is given by n equals n max. N max is a number I calculated up here, and that is the total number of nodes in the y direction, so the vertical nodes. And then the same goes for the horizontal x direction nodes. We've got m equals 1 and m equals m max, which represent the left and right sides of the bar. And all of these equations are the equations from the node configuration from table 4.2. This else option is for the interior node. And so all of these numbers are the coefficients for the temperatures for an interior node. So now if I calculate the temperature vector, I can just use this little linear algebra shortcut in MATLAB, basically taking the inverse of the A matrix, multiplying it on both sides, and you can find the temperature vector that way. And so then I plotted the temperature profile, and I'll show you that in a second. And then finally, I calculated the convection heat transfer rate per unit length by using Fourier's law and dividing by some arbitrary bar length, which were not given. So if I run this, you can see that I get this temperature profile, which makes a lot of sense. You can see that the right side here, which is exposed to the cooler fluid, is the coldest area of the bar, represented by this blue color. And that temperature slowly increases as you move to the left and also up and down. And so these surface nodes on the top and bottom here are all at 473 Kelvin, as they should be. They're constant throughout. the problem throughout the surface. And so what I wanted to show is that if I increase or decrease this spacing, my results here will change drastically because the number, well, not too drastically, but the number of nodes will decrease and my accuracy will decrease if I increase the spacing parameter. And so let me show that. Um, if I make this 0.09, you can see that my temperature profile becomes a lot more square and less smooth. And so let me change this to figure 2. I'll bring up the proper spacing, run, and then I'll just change it one more time and show you what happens when you use an even smaller spacing. Figure 3, we'll call it. And you can see that that third time that I just ran the program there took a little bit longer. And that's the trade-off you get for higher accuracy. When you decrease your spacing parameter, um, your accuracy will increase, but your computing time and the total computational power will increase, unfortunately. But you can see here that as I decrease the spacing dimension, my temperature profile becomes more and more smooth and continuous appearing. And so obviously this figure on the right side here is the most accurate model because we are using so many nodes. You can see them all shown by these black dots. And so just one more thing, when I go back to um, the proper spacing, I'll show you that temperature profile. You can see here those values in Kelvin, which are correct. And so that is how you solve problem 4.065. You can see that the total heat transfer rate per unit length of the bar is around 2.38 or 2.39. That's also given by the MATLAB script over here. You can see QComp 2.38 kilowatts per meter. So that is how you solve problem 4.065. Thank you.